Hello and welcome to our lesson about continuity. So take a pen right now or a pencil and draw a line with me. Look, just any type of line. It can be wavy, anything. You might notice something. I never removed my pen in order to draw this. Now let's draw something else. Let's draw a line. Remove the pen for a dot and then continue the line. In this case, look, I have an empty part here. I actually removed my pen for a little while. So, this is what we call a discontinuity. So this line is not continuous. However, in the first line I drew where I did not remove my pen anywhere, we call this continuous. So this was just an introduction to continuity. Let's look at the formal definition. A function f is continuous at a number a if the limit of f of x as x approaches a is equal to f of a. So how can we tell if this is the case? So we have three conditions, and all three conditions must hold. Not one, not two, all three of them. Let's see what the first one says. F of a is defined. Let's look at this graph right here. We see that this is a, and this up here is f of a, this point in blue, and it is indeed defined. Now, let's look at the second condition. The limit of f of x as x approaches a exists. When does a limit exist? A limit exists if the right-hand limit, so the limit of f of x as x approaches a from the right, is equal to the limit of f of x as x approaches a from the left, and it's equal to a number L, let's say. Now that's the second condition. So as we can see, as we approach a from the left, and as we approach it from the right, we are reaching the same point. So the limit from both sides are equal. Now the third condition is that the limit of f of x as x approaches a equals to f of a. And as we just saw right now, as we approached a from both sides, the point that we reached right here, this is f of a. So this third condition also holds. And this is when we say that this function f of x is continuous at point A. Just to keep in mind that this definition up here, a function f is continuous at a number a, this refers to continuity at a point, because we are finding whether the function is continuous at point A, not on all of its domain, but we will indeed learn how to find whether a function is continuous on its entire domain in a few minutes. Now, of course, we also have what we call continuity from the left and continuity from the right. So a function f is continuous from the right at a number a, again, this is at a point, if the limit of f of x as x approaches a from the right equals to f of a, and f is continuous from the left at a, again at a point, if the limit of f of x as x approaches a from the left equals to f of a. So let's check where we have continuity from the left or the right. Let's look at point A, which we have right here. So the limit as x approaches a from the left is equal to f of a, because we have this filled in circle. This is f of a. So we can write the limit as x approaches a from the left of f of x is equal to f of a. Now let's try from the right. If we approach a from the right, we do not get f of a. Therefore, in such a case, we would say that the function is continuous from the left. Now let's look at point B. If we approach point B from the left, we do not get f of b, but if we approach point B from the right, we get f of b. So let's write this down. The limit of f of x as x approaches b from the right is equal to f of b. So the function is continuous from the right at b. And in the previous example, we can add here at a. So this is what we call left and right continuity. Now let's check when a function is continuous on an interval. So a function f is continuous on an interval if it is continuous at every number in the interval. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. So this will get clearer through an example which we will do later on. However, for now, just keep in mind that if a function, let's say this is a function f of x, is continuous over the interval with closed brackets from a till b, so it is continuous at every point inside. So if we were to do continuity at a point, so use the above definition that we learned before, at every point in between A and B, the three conditions we learned before would hold. So as the definition says, the function would be continuous at every number in the interval. Now regarding the last part of the definition, again, I will explain it using an example later on. Now let's look at discontinuities. So we have three types of discontinuities. The first one is what we call a removable discontinuity. So as the name suggests, it's as if you had a point right here, but you simply removed it. This is how it looks like in graph A. Let's look at the graph B. We had a point right here, we removed it. And look where we put it at somewhere else in the graph. But regardless whether we have this other point or not, the fact that we have a point that is removed from the curve, this means that we have a removable discontinuity. Now, an infinite discontinuity is when the limit of the curve approaches infinity. It does not have to go to infinity on both sides, so even if we have one side that goes to infinity, this would still be an infinite discontinuity. Now, a jump discontinuity, as the name suggests, we are jumping. So there's a jump here, a jump here, a jump here, a jump here. So as the name suggests, this is what we call a jump discontinuity. Now, given this graph, which is from page 115 in the book, let us identify the discontinuities. So let's begin. Let's start with at the point x equals to 1. We can notice here that there's a point that was taken off, that was removed, because we have an empty dot here. Therefore, at x equals to 1, we have a removable discontinuity. Now, at x equals to 3, we were at this point here, and then to continue drawing the graph, we jumped up till here. I said the word jump, so here we have a jump discontinuity. Now let's continue. At x equals to 5, I had a point here that was removed and placed up there. So a point was removed, so we have a removable discontinuity. And I just wanted to point out that at x equals to 3, as x approaches 3 from the left, so the limit as x approaches 3 from the left is equal to f of 3. So at x equals to 3, we have continuity from the left. Now let's proceed to an example. Show that the function f of x equals to 1 minus square root of 1 minus x squared is continuous on the interval -1 till 1, including both endpoints. So, this is what I was telling you before. I will explain continuity on an interval using an example. So first of all, we said for a function to be continuous on an interval, it has to be continuous on every point in the interval. So, let's apply the definition. So the first condition is that f of a exists. The second is that the limit of f of x as x approaches a exists. And the third condition is that the limit of f of x as x approaches a is equal to f of a. So what we will do, we will find the limit of f of x as x approaches a. Let us find it. So the limit of f of x as x approaches a is equal to the limit. We plug in f of x. So 1 minus the square root of 1 minus x squared as x approaches a. Now we are working at every point inside the interval. So just keep in mind that in here, -1 is less than a less than 1. We will deal with the endpoints 1 and -1. We will deal with them later. So let's start first with any point inside the interval. So let's compute the limit of 1 minus the square root of 1 minus x squared as x approaches a. So, as usual, what we do with limits is we can separate them using limit laws. So since we have minus here, we can do the limit of 1 as x approaches a minus the limit of square root of 1 minus x squared as x approaches a. So let's compute each of these limits. The limit of a constant is the constant, and the limit of square root of 1 minus x squared as x approaches a. We can plug in a to see what this gives us. So this gives us 1 square root of 1 minus a squared, which is the answer of this limit. So we get 1 minus the square root of 1 minus a squared. So now we were able to verify that the limit exists. Now let us check if f of a exists. So our second condition, check mark, we did it. Let's look for f of a. F of a is equal to 1 minus the square root of 1 minus a squared. It exists. First condition verified. What do we notice? We notice that the limit of f of x as x approaches a is equal to f of a. So let's write this down. The limit of f of x as x approaches a is equal to f of a. Now this shows that we proved that the function is continuous on the open interval -1 till 1. But we need to deal with the endpoints. So we need to deal with the points x equals to -1 and x equals to 1. How do we do that? For a function to be, let's say this is our function, I'm just drawing a random graph. If this is point A here and this is point B here, for a function to be continuous also on the endpoints, the limit as x approaches A from the right, because we're going to A from the right, of the function should be equal to f of A, and the limit as we approach B from the left should be equal to f of b. So let's try to prove that. So our lowest endpoint on the left is -1. So as we approach -1 from the right, let's compute what we get. This will give us the limit of 1 minus square root of 1 minus x squared as x approaches negative 1 from the right. So what we do in such a case, we can try to plug in to see what we get. We get 1 minus square root of 1 minus negative 1 all squared, which is equal to 1 minus square root of 1 minus 1, which is equal to 1 minus 0, which is 1. Now let's find f of negative 1. F of negative 1 is 1 minus the square root of 1 minus negative 1 all squared, which is also equal to 1. So the limit of f of x as x approaches negative 1 from the right is equal to f of negative 1. So we have dealt with the left endpoint. Let's deal with the right endpoint. The limit of f of x as x approaches 1 from the left is equal to the limit of 1 minus square root of 1 minus x squared as x approaches 1 from the right, from the left, which is equal to the limit. Actually, we can plug in now to see what we get. It gives us 1 minus square root of 1 minus 1 squared, which is equal to 1 minus square root of 1 minus 1, which is equal to 1 minus 0, which is 1, and this is our answer. Now let us find f of 1. F of 1 is 1 minus square root of 1 minus 1 squared, which is equal to 1 minus 0, which is 1. So the limit of f of x as x approaches 1 from the left is equal to f of 1. So now we have dealt with both endpoints, and therefore we have proved that the function is continuous. So we write, therefore, f of x is continuous. Don't forget to mention the interval, which is negative 1 till 1. Now let's look at some properties of continuous functions. So if f1 and g are continuous at a and c is a constant, then the following functions are also continuous at a. So we get that f plus g is also continuous at a, f minus g, a constant c times f times g, and f divided by g as long as g is different from 0, because we cannot have a denominator of 0. Now the following types of functions are continuous at every number in their domains: polynomials, rational functions, root functions, trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions. Now let's look at an example that applies both of these theorems. So where is the function f of x equals to ln x plus arctan of x divided by x squared minus 1 continuous? So first I will just rewrite it here. And now we might notice that we can in fact simplify the denominator. So we can write the denominator as x minus 1 times x plus 1. Now let's try to find where it is continuous. Where is ln of x continuous? Ln of x is continuous when x on its domain, but now what is its domain? Its x is greater than 0. Now let's look at arctan. Just a reminder that the graph of arctan looks something like this. So its domain is in fact all real numbers. Now in the denominator, x minus 1, also its domain is all real numbers, and x plus 1 too, but keep in mind that the denominator cannot be 0. So x minus 1 times x plus 1 should not be 0. Therefore x minus 1 should be different than 0, and x plus 1 should be different from 0, so x should be different than 1, and x should be different from negative 1. So keeping all of these conditions in mind, let us find their intersection. So their intersection is where the function f of x is continuous. So this will give us that the function f of x is continuous on 0 till 1, because x is greater than 0, but x also cannot be 1, union 1 till infinity. Now let's move on to this theorem. If f is continuous at b and the limit of g of x as x approaches a is equal to b, then the limit f of g of x as x approaches a is equal to f of b. In other words, the limit of f of g of x as x approaches a is equal to f of the limit of g of x as x approaches a. Basically, what we are saying is we can switch the limit and f. Let's look at an example to make this clear. So, evaluate the limit of arc sine of 1 minus square root of x divided by 1 minus x as x approaches a. What we can do in such a case is we can switch the arc sine and the limit. So we can write arc sine of the limit of this entire fraction, 1 minus square root of x divided by 1 minus x as x approaches 1. And then we compute the limit. So if we were to plug in, we would get 1 minus 1 minus square root of 1, which is 1 minus 1, which is 0, divided by 1 minus 1, which is 0. So whenever we have 0 over 0, let us rationalize. So we can multiply this by 1 plus square root of x in the numerator and in the denominator. So this gives us, in the numerator, 1 minus square root of x times 1 plus square root of x is 1 minus x. And in the denominator, we are left with 1 minus x times 1 plus square root of x. And this is the limit as x approaches 1. We notice that we can cancel 1 minus x from the numerator and the denominator. We are left with arc sine of limit of 1 divided by 1 plus square root of x as x approaches 1. Let us plug in. If we plug in, we get 1 divided by 1 plus square root of 1, which is equal to 1 over 2. So arc sine of 1 over 2, plug this in on your calculator, you get pi over x. So this is how we solve such types of questions. Now let's move on to another theorem. So if g is continuous at a and f is continuous at g of a, then the composite function f of g given by f of g of x, and this is just a different notation, is continuous at a. So let's say h of x equals to sine of x squared. We know that h of x, we can write that as f of g of x. So if f of x is equal to sine of x, and the reminder that the graph of sine of x looks something like this, its domain is all reals, and the graph of g of x, let's say g of x is x squared, the graph of x squared looks something like this, and again the domain is real, all real numbers, then h of x, which is equal to f of g of x, is continuous on all real numbers.